There's a hole in space 330 million light-years wide. Almost no galaxies. Almost no stars. Just empty darkness. Astronomers call it the Boötes Void. And according to our models of how the universe formed, it shouldn't exist. In 1981, astronomer Robert Kirshner was mapping galaxy positions using a telescope in Arizona. He was creating a three-dimensional map of our local universe. When he plotted the data, he noticed something strange. A massive region with almost nothing in it. Most regions of space this size contain between 2,000 and 10,000 galaxies. The Boötes Void contains only 60. That's 97% emptier than it should be. Kirshner thought it was an error. He checked the data repeatedly. The void was real. The Boötes Void is located roughly 700 million light-years from Earth in the direction of the constellation Boötes. Its diameter is approximately 330 million light-years. To put that in perspective, our entire Milky Way galaxy is only 100,000 light-years across. You could fit 3,300 Milky Ways in a straight line across this void. Light traveling at 300,000 kilometers per second would take 330 million years just to cross it. If you started traveling from one side at the speed of light when dinosaurs walked the Earth, you still wouldn't reach the other side today. It's one of the largest known structures in the observable universe. The void isn't completely empty. Surveys conducted between 1987 and 2014 identified exactly 60 galaxies inside the Boötes Void. Most are small dwarf galaxies. For comparison, the same volume of normal space would contain 2,000 to 10,000 galaxies. These 60 galaxies are distributed strangely. They cluster near the edges of the void. The center is almost completely empty. In 1997, astronomers using radio telescopes found 15 galaxies clustered in a small tube-like structure running through one section. But aside from that, the void remains profoundly empty. The few galaxies that exist there show unusual properties. Many have lower metallicity than expected. This suggests they formed fewer generations of stars. They're underdeveloped compared to galaxies in normal regions of space. According to the Lambda CDM model, the standard model of cosmology, matter in the early universe was distributed almost uniformly. Small density fluctuations, about 1 part in 100,000. Over billions of years, gravity amplified these tiny differences. Dense regions pulled in more matter and became denser. Less dense regions lost matter and became voids. But this process has limits. Computer simulations show that voids larger than 150 million light-years are extremely rare. They require very specific initial conditions. A void 330 million light-years across is statistically improbable. The probability calculations suggest we shouldn't observe something this large in our observable universe. Dr. Greg Aldering from Lawrence Berkeley National Laboratory ran simulations in 2010. His team modeled void formation over 13.8 billion years. Voids the size of Boötes appeared in less than 1% of simulations. And when they did appear, they formed differently than what we observe. To understand why the Boötes Void is strange, you need to understand the cosmic web. Galaxies aren't randomly scattered through space. They form a pattern. Long filaments of galaxies connected by nodes. Between these filaments are voids. This structure resembles a three-dimensional spiderweb. The cosmic web formed because of dark matter. Dark matter created gravitational scaffolding in the early universe. Normal matter followed this scaffolding. Galaxies formed along the densest regions, creating filaments. The spaces between filaments became voids. Most voids are 30 to 150 million light-years across. They're bordered by galaxy filaments. The Boötes Void is more than twice as large as the biggest voids predicted by models. It's an outlier, an anomaly that demands explanation. Theory 1, rare but natural. Some cosmologists argue the Boötes Void is simply a statistical fluke. Extremely rare, but not impossible. In an observable universe containing trillions of galaxies, unlikely events occasionally happen. We might be observing the one-in-a-million void that physics allows but rarely produces. Theory 2. Multiple smaller voids merged. Another hypothesis suggests the Boötes Void isn't a single structure. It could be several smaller voids that merged over billions of years. As galaxies moved away from underdense regions, neighboring voids expanded and eventually connected. This would explain its unusual size. But observations don't show clear boundaries between merged regions. Theory 3. Dark energy variations. Some physicists propose that dark energy, the force accelerating the universe's expansion, might not be uniform. If dark energy was slightly stronger in the region that became the Boötes Void, it would have pushed matter away more aggressively. This could create a larger void, but we have no evidence that dark energy varies across space. Theory 4. Primordial origin. The most radical theory suggests the void formed from an extremely rare fluctuation in the moments after the Big Bang, a region where quantum fluctuations created an unusually large underdensity. This would mean the Boötes Void is a fossil from the universe's first microseconds, a frozen imprint of conditions 13.8 billion years ago. The Boötes Void isn't the only supervoid astronomers have discovered. In 2004, researchers identified the CMB cold spot, a region of space approximately 1 billion light-years across with fewer galaxies than expected. It creates a cold spot in the cosmic microwave background radiation. In 2015, astronomers discovered an even larger structure, the Eridanus supervoid, roughly 1.8 billion light-years in diameter. It may explain the CMB cold spot. But like Boötes, its size challenges cosmological models. These discoveries suggest supervoids might be more common than our models predict. Either our understanding of structure formation is incomplete, or we're missing something fundamental about how matter distributed itself after the Big Bang. The Boötes Void presents a significant challenge to the Lambda CDM model. This model has successfully predicted many cosmic structures: galaxy clusters, filaments, normal-sized voids, but struggles with supervoids. If supervoids are common, we may need to revise our understanding of several things: the initial density fluctuations after the Big Bang, the properties of dark matter, the behavior of dark energy, or even the rate of cosmic expansion. Some cosmologists suggest these voids indicate our models work well on small scales, but break down on the largest scales. The universe might be lumpier on cosmic scales than we thought. Matter might be distributed less uniformly than the Lambda CDM model assumes. The Boötes Void presents a significant challenge to the Lambda CDM model. This model has successfully predicted many cosmic structures: galaxy clusters, filaments, normal-sized voids, but struggles with supervoids. If supervoids are common, we may need to revise our understanding of several things: the initial density fluctuations after the Big Bang, the properties of dark matter, the behavior of dark energy, or even the rate of cosmic expansion. Some cosmologists suggest these voids indicate our models work well on small scales, but break down on the largest scales. The universe might be lumpier on cosmic scales than we thought. Matter might be distributed less uniformly than the Lambda CDM model assumes.